in this part, we'll start taking a look at what are the different aspects of SQL that you have to keep in mind when dealing with large data sets. So before we get there, let's just spend a bit of time trying to understand what happens when an SQL statement gets executed behind the scenes. So first and foremost, the different syntaxes, we've already seen that. So we saw the fact that you need a select statement to express a projection, a from which tells you which tables or which data sets that you're operating on, a where clause to allow you to filter, basically select the data sets that you're take forward for processing. Optionally, you could have some set operations, you could have some join operations. If you do aggregations, then you need a group by syntax, and if you do a group by, then you might think about having like a having as well. A having is basically, it's like a where clause, but it's like a selection, but it applies on top of aggregated data. So that's the syntactical sugar corresponding to what SQL is. So if you break down a typical SQL statement, it looks like this. So select r.a from r in the join s on the column values being the same, r.b equals s.b, where s.c equals 10, right? So that's your SQL statement. So how does a typical SQL engine go about planning for this, right? And here's where we start to get to nuances of individual databases, the backend engines, and all of that. For the purposes of this course and this particular week's lectures, we'll predominantly be only focused on Spark SQL. A lot of what I'll be talking about actually apply to any other database as well. The theories are the same, the concepts are the same. The implementation, the how part of it could change in some cases, rather than most cases. The syntax will definitely change. How you express a certain kind of join will vary from one database to another. But the key is that if you understand the foundations here, you should be able to take that learning to any other SQL engine without a problem. One significant thing that I wanted to mention here is that Spark SQL by itself is not a database. It's actually an SQL processing engine. So, and that's why you have to really think, really be precise, right? SQL is actually a programming language. It is not a stateful storage system. In some cases, people have mistakenly referred to SQL as a database, and they're not wrong because they typically come in from that from having had experience with Microsoft's RDBMS product, which is called a SQL Server, and in short, sometimes it's called as SQL, right, or SQL. That is unfortunate because the naming overlaps with the SQL standard, which everybody implements. So you should learn to set that aside or learn to understand the context based on what the conversation is about. But in general, the SQL language is a front-end specification system, right? It doesn't really talk about the backend. It doesn't talk about what is the backend storage engine looking like, how is it optimized, etc. And there are many options, obviously, for what the backends can look like. But for the most part, the front end is where the data processing happens, right? What I mean by that is, I'm not talking about a physical system like a front end, but the front interface, the programming interface determines the data processing, right? It's not the back end. It's not the way it's implemented that tells you that gives you the functionality or the flexibility. It's the language syntax itself that gives you the power, right, that you need. So Spark SQL has implemented its own SQL execution engine, and that has its own design pros and cons. But that's geared towards making big data SQL be much faster and simpler to use than previous attempts that were made until that point that Spark SQL evolved. So keep that in mind. you would typically pair Spark SQL with some kind of a data store anyway, right? It could be a NoSQL system, it could be a relational database like an RDBMS, doesn't matter. But you would not use Spark SQL by itself, you would end up using Spark SQL with some kind of a store. Notice that the store that Spark SQL needs for its execution need not be a database in the classical sense. It could be a NoSQL system, like I said. It could also be a file system, right? It could also be like another Hadoop distributed file system. It could be a object store like the cloud storage systems, etc. Okay, so let's take the SQL statement. Let's parse it and see what happens. The first step that any SQL engine does is something called as parsing. That's what's responsible for figuring out if syntactically you've entered valid, like a valid statement, or did you misplace like a comma, or did you use the wrong keyword at the wrong place, etc. Like all of those syntactical checks actually happen as part of the parsing. So once the parsing happens, then that textual form of what you want to do gets translated into a tree, which is actually the relational algebra tree, which basically is the first internal representation, which is canonical. Canonical meaning it's a relational algebra form, so it's easily understood or understandable by anybody else who understands relational algebra. So you would think that if all RDBMSs support relational algebra, then the canonical model should be the same. So why can't they more easily interoperate with each other? That's a valid thought, but like I said, the front end could vary, right? The front end language, syntax, those things can vary. Yeah. So once the relational algebra's syntax tree is constructed, then we can start to look at what is it to do next in terms of planning and execution. So there are actually multiple steps that happen here in this stage. Depends on the maturity of the SQL engine. It could be ranging from just a simple straightforward planning to, in some cases, creating what's called as a logical plan, then taking a stab at optimizing it, with creating the more detailed optimized logical plan, and then finally thinking about how to physicalize it into like a set of operations that happen in the backend. So it depends on the engine, but in general you will have planning and optimizing typically happen together. Okay, so what could be, for instance, one interesting optimization that we could do here? It comes down to the ability to look at the relations which are being specified, the relational operators which are actually present here. So what the optimizer, and in this case the optimizer that's embedded within the SQL engine, what it starts to do is it starts to look at options for me to reorder operations such that I can have the least amount of data flow up, right, through the tree. So the classical way in which the parsing happens need not actually be the final way in which it executes, right? Because there are optimizations like this which are possible. So what optimization am I talking about? Notice that I really want to filter on a specific access to the data. By the way, going forward, let me just use the SQL way of explaining this as opposed to the mathematical relational algebra way of explaining this. So it's easier for you to follow along. So what I want to do is filter on a column, right? The column, in fact, filter on a specific value of a column, s.c equals 10. But I am doing this in my first instance of the relational tree after the join operation is performed, which means I take all of the rows, all of the data sets of S, all of the rows of R, all of the columns of R, all of the columns of S, merge it all together with a commonality constraint on the column B for each of those two tables, and then I'm applying the filter saying that I'm interested only in those columns of S rather those values of S, records of S, for which the value of column C is 10, which kind of seems wasteful, right? If that's how it's going to get physically executed, that's a lot of wasted effort, because all those joins for those data records where the value for C is not 10 is not required. So why do that after? So here's an option. Here's a simple way I can push down a predicate. So what I've done here is taken this kind of a clause. The clause is called as a predicate, and I've pushed it down through the join operator into the branch that on which it's applicable. So in this case, S branch is what I want, and the C column filter is what I want to push down. So in doing that, the new join subtree looks like this. Instead of directly reading R and S, it continues to read directly R, but then the S branch goes through the predicated filtering, and the predicated filtering is a selection operation, which then gets the set of records which are matching the filter clause. So this is much better in terms of physically executing as and when it happens. And then finally the projection, which basically is the column A for the R table. That's what's getting projected out, so that's coming out here. Notice that also can be predicate pushed down through the join, such that the join does not need to bubble out any other column except A and B. Like B is also required, obviously, because the join is on B, right? But you don't need any of the other columns. It could be C, D, E, etc. Right? So that avoids the extra data reads which could be happening there. So yeah, so multiple rounds of optimization happen. I'm just giving you like a hypothetical example here. In practice, once those logical plans are iterated upon and finally the final version of the plan is arrived at, then that gets physicalized, meaning that it's translated into the how aspect of it, right? And that how aspect is what dictates the performance of the entire operation. So we call it physical plan materialization. You could also call it, you could just refer to it as a physical plan. So when it comes to the physical plan, here each database really varies in terms of its options for how to physicalize a particular operation. But think of it as there are a bunch of specific functions that get called within the context of the language in which that particular backend is written. So in the world of Spark SQL, everything is written in Java, right? In the world of, let's say, Oracle, that's also written in Java. In the world of Postgres, it's all written in C. So yeah, these things vary based on what foundational technologies get used. So the crux of what happens in the physical plan materialization is that the nature of the operation that needs to be performed to match the logical plan is chosen in such a way that firstly the operation needs to be performed. We're expecting some functionality to happen, right? So you can't change that. So the functionality happens, and it chooses that operation type to implement that logical operation to achieve that outcome in such a way that the physical operation type is the least cost. So this notion of cost is interesting, and that's something that you should all start to internalize. So in deciding how to do a specific logical operation, the database effectively says, I'll have the thinking to happen by me, like you don't have to worry about it. But then you should ask naturally this question out of skepticism: how does it know what I know? Right? How does it know to look at the data set with a certain lens, with a certain appreciation of the size of the data, the distribution of values in the data, the dependencies between the different data elements, etc. All of that is something you know as a developer. How does the data SQL engine know? And that's where there is a lot of detail level modeling that you need to think about. So we're going to spend a good 1 hour or so about it on this exact same topic coming up, right? As soon as this video is done. But yeah, in effect, you're going to have to think about cost, and that cost is by default modeled for you, and the default way in which the cost is modeled is usually not right. It's all right to just get you off the ground and get you an answer, and in most cases where the data is small, the default cost modeling is usually sufficient to not be egregiously bad, meaning it's not going to result in some dramatically bad execution plans compared to the normal, compared to something if it was chosen optimally, if it had all the information at its fingertips, if the data set is small, right? But if the data set is large, then there is a huge difference between the default cost modeling versus something that you can influence with the right information from the domain. So this is where a lot of engineering effort typically goes in when starting to build SQL pipelines for big data. Alright, so the cost is actually being computed for every step in the logical plan. And when it's computed, the lowest levels, right, because it's a tree, the lowest levels are usually more accurate, and the higher levels are estimates built on top of the lower levels. So let me take an example, right? So when I say the cost of reading S is the cost of reading those many number of rows from disk, right? That's the cost effectively. That cost has a certain performance characteristic attached to it. Let's assume so what happens is all of these read operations are expressed as fundamentally units of reading of one record of 1 kilobyte from the disk. So it's all expressed relatively, not in absolute terms. So that aside, when I do a filter which says that I'm only interested in column value 10 for C, column C, then the cost of the operation from that point on for this branch related to S is already filtered, right? It's already lower than what it would be if this filter was not applicable. Let's assume it's effectively doing some filtering such that only 10% of the data goes through. How does the SQL engine, which executes, know only 10% of the data is actually going to go through? Or what percent of the data? Let's assume it's 1%, right? How does it know only 1% goes through? It's actually not possible for it to know without an iota of doubt, but it can estimate, and the way it can estimate is by looking at column distributions for all columns in a table, and in doing so, it constructs in its own memory a footprint about how this specific table actually looks like if you were to describe it using some summary statistics. So that is what is helpful for it to figure out. If I do a filter like this, then I'm effectively filtering out 99% of the data and only 1% comes through. And that 1% means that the size of the data set at this stage is dramatically different compared to the size of the data here. And that's what allows it to actually do, various levels of further optimizations in terms of the type of join to perform, etc. So we'll take a look at that, in a couple of slides. Yeah. So long story short, cost is an important modeling decision. Many SQL developers don't know this, but the backend actually makes these very simple foundational mistakes, right? I wouldn't say mistakes, I would say modeling decisions on cost, which for big data purposes is usually not something that you should rely upon. For small data, it doesn't matter. For big data, it definitely matters. Okay, so two things we spoke about here. The cost model. Actually, there's a counterpart to that which is called as rules. The rules are what is responsible for doing more, more examples of this predicate pushdown, right? Like that, the bunch of rules which say if my cost is very low for doing a specific operation and if the data set is small, then I have a bunch of algorithms that are available for me to use in order to execute the join or the group by, I don't use any of that because the data set is large. So those are all rules, right? And those rules basically dictate what kind of a data flow happens. But the input to those rules are usually themselves stats, and those stats are being collected on top of the data set that is required to be analyzed. So stats and rules, they feed into the physical plan generation step. So why do we care about what is the cost of a specific operation? The cost determines performance. So if you don't get the cost right, if you don't get the modeling right, in fact, to be very precise, if you don't transfer the knowledge that you have about the data set, the operation that you're performing, to the engine, right, so that the engine can decide the how in a way that's a lot more intelligent than the default behavior, then you practically kill the problem, because the scale at which big data operates is so large that even small differences in performance gets exacerbated over a period of time. So keep that in mind. And again, why do we care? We care because OLAP, which is the part of the spectrum that we're dealing with when it comes to large-scale data analysis, is about fundamentally reading data, not writing, not updates. So if you look at the CRUD model, the R is the most important for OLAP, and therefore the typical statement that you end up spending a lot of time in terms of optimizing, in terms of writing, is the select statement, not the insert, not the update, not the delete. So that's why we are spending some time on this. And knowing how SQL queries work, select statements work, is very critical. Okay, so let's pause here. I'll come back to types of joins in the next video.